Hello everyone, I am Jubea faculty at Silvers Public School, KOZHIKODE. In the last sessions, we have discussed about the atomic size, physical properties and electronic configuration of d block elements. Today, I am going to deal with ionization enthalpy and oxidation state. Let us see what are the learning objectives in this session. We will be going with the variation in the ionization enthalpy, that is along the period and down the group. We will be also understanding the new terms like the first ionization enthalpy, second ionization enthalpy and their variation. We will be discussing oxidation state, that is in the d block elements they can form higher oxidation state. There are certain metals which are having even zero oxidation state, and in certain compounds like oxides and fluorides they are even showing highest oxidation state. So, all these variations will be explained in this session. Now, let us see what is this ionization enthalpy. To understand about ionization enthalpy, in the last video we have discussed atomic size. We have given a very simple example, which is your classroom and your auditorium. Now, here also let us move on to the same example to understand this term ionization enthalpy. Ionization enthalpy, by definition, you might have heard this. What is ionization? It defines like it's the energy needed to take an electron from the outermost shell of an isolated gaseous atom. This is the definition what must be studied even in the lower classes. So, let us understand this in a more detailed manner. Now, when you consider a classroom, as I have explained, the teacher is the center, the students are being seated in the benches, and always the teacher have a control on the students who are sitting at the last row. If a student needs to move out from the class, he or she should ask permission, or someone should come from outside and ask permission to the teacher to call a student from the class to move outside. So, here there is a change of energy. Like that, inside an atom we have the nucleus. In the class we have the teacher, in the atom we are having the nucleus. The nucleus have a good control on the electrons in the outermost shell. So, if an electron needs to move out, we need certain energy to take that electron. That energy which is needed to take the electron is called the ionization enthalpy. The word enthalpy is energy change. Now, the classroom is smaller in size, you need more energy. Now, similar manner, you consider the same teacher taking a class in the auditorium. The auditorium is very big. So, what happens? If a student needs to move out, he or she cannot go and ask the teacher who is teaching in front. They may move out from the auditorium. Especially when the programs are going on in auditorium, students will just move out from the auditorium, isn't it? Why? It is so big. So, like that, the same manner inside an atom, when atom is very big, what happens? The number of shell is more. Then we have studied that the effective nuclear charge is outweighed, or the shielding or screening effect outweighs the effective nuclear charge. So, what happens here? When the size of the atom is bigger, it's very easy to take the electron. So, these are 2 points that we have to keep in mind. When the size is smaller, you need more energy to take the electron. When the size is bigger, we need only very little energy. So, this is a need of energy, isn't it? You need an energy to take the electron. So, this ionization enthalpy is always a positive term. So, we will just once again go on to the definition. I have shown it in an equation manner here, that M is generally who gives electrons? Metals gives electrons. And whenever they gives electrons, what charge they do have? They have a positive charge. So, it is very good to take an example as a metal. Metal needs ionization enthalpy, it changes to M plus. So, it is giving an electron there, it is changing to an ion. So, we can change this definition in another manner. Ionization enthalpy is the energy needed for a metal to become a metal ion. But the best manner to define is the earlier definition which is shown here. Now, let us move to the factors affecting the ionization enthalpy. The most important factor is the effective nuclear charge. Second one, the screening or the shielding effect. And the third one is half-filled and completely filled subshells. I have explained this with an example that how the effective nuclear charge and your shielding effect affects the ionization enthalpy. And now what about this half-filled subshells, completely filled subshells? You have studied the half-filled and completely filled stability, where we explain about the exchange energy and their extra stability. Now we will move on to ionization enthalpy along the period. So along the period we know that the size of the atom will decrease. Why is it decreasing? The shielding or the screening effect have an effect on it. What is the effect? The effective nuclear charge outweighs the effective screening effect. You always have a screening or a shielding effect. So the effective nuclear charge will surely outweighs the shielding effect. Now similarly we will move on to the change in ionization enthalpy down the group. What happens down the group? Along the period we have seen it is increasing, and we told that effective nuclear charge outweighs the shielding effect. So size is decreasing. But what happens in the atomic condition when you consider down the group? When you consider down the group, it's just the opposite, isn't it? The shielding effect outweighs the effective nuclear charge. So when the shielding effect outweighs the effective nuclear charge, what is happening there? The size is bigger and we need only very little ionization enthalpy. Down the group, we'll see that increase in atomic size is there, increase in electron-electron repulsion. So what happens? There's an increase in shielding effect. That is, shielding effect outweighs the effective nuclear charge. And what happens to our ionization enthalpy? Ionization enthalpy decreases. So these are the conditions that ionization enthalpy along the period and down the group. Now let us move our attention to the D block elements. To moving on to the D block elements, we have to consider the 3D series. We know that there also we are considering along the period and down the group. But down the group, you have a lot of variations because of the lanthanoid contraction, which was explained in the earlier session. Along the period also, you can see a lot of variation. Now, I'll stick on to more to along the period of the D block elements. Along the period, we consider 3D series, which is a very important series in the D block. When we consider 12th standard, most of the topics are related with the 3D series. You should know how to write the electronic configuration of 3D series, and it was discussed in the part 1. So from scandium to xenon, you should know the electronic configuration. After understanding electronic configuration, we have to see how the electrons are being taken. Where do you take the electron from the scandium, xenon, all these elements? From which orbital are you taking the electrons? We take the electron from the outermost shell. That is what you called as the ionization enthalpy. So let us have a look. How are we going to take the electrons from the outermost shell? And is it just the electronic configuration that affects the ionization enthalpy, or does the atomic size affect it? This was the atomic size along the 3D series. In this graph, we have seen that first it decreases, then becoming constant, then increase. So always keep in mind, when you are going to explain the ionization enthalpy of the 3D series, you should know more about the atomic size as well as the electronic configuration. Both should go hand in hand. Then only you will understand the variation in the ionization enthalpy. Now you might have heard about the terms like first ionization enthalpy, second and third ionization enthalpy. What does it mean? What is ionization enthalpy? It's the energy to take the electron. So from an isolated gaseous atom, if you are taking one electron, what happens to it? It becomes metal ion, M+. Now again from M+, if you take one more electron, it becomes M2+. Again from M+, if you are taking, it becomes M3+. So each time to take the first electron, you call it as first ionization. To take the second electron, you call it as second ionization enthalpy. And to remove the third electron, you call it as the third ionization enthalpy. Just see, from M is an isolated gaseous atom, it is changing to M+, M2 plus and M3 plus. So what happens to the size of the atom? The size of the atom decreases, and what happens to the ionization enthalpy? Generally, ionization enthalpy increases for the first, then second will be more, and then to the third. So third ionization will be always generally very high. But there are cases where the third ionization enthalpy is lesser. It is based on, as I told you, the atomic size, R-full stability, completely full stability, and so on. So let's have a good look with the ionization enthalpy along the 3D series of your D block elements. Now we have a look at the electronic configuration. We have seen how the atomic size varies along the 3D series. This is a look with the electronic configuration. Here just see scandium, argon 3D1 4s2, titanium, argon 3D2 4s2. I have explained how to understand the electronic configuration with a simple trick in part 1. So when we go on, our energy is the energy needed to take the outermost electron, isn't it? So in all the cases we are seeing that most of the cases the outermost electrons are completely filled. Now which is the outermost shell here? It's a 4s. 3D is the penultimate shell. So you are going to take the electron from 4s. In all these cases they are completely filled, but here it is half filled. Whenever it is completely filled, you need more energy. So generally the ionization enthalpy will be going in a higher manner. It will be increasing. Now the electron is taken from the outermost 4s. In all the cases it is completely filled. Now just see in case of Mn it is 3d5 4s2. Zn 3d10 4s2. Mn is having R-full stability as well as outermost it is 4s2 completely filled. Zn completely filled 3d and an half completely filled 4s. So the highest ionization enthalpy will be for Zn. It will be just an increasing curve or an increasing manner line in when you see the graph, and will be highest at the Zn. So the first ionization enthalpy will be very high for Zn. We will just have a look at the graph. This is the first ionization enthalpy. I have already explained it. Energy required to remove the first electron from an isolated gaseous atom. This is your metal, or you can consider an atom. You are removing an electron, it becomes M plus. Now this is a graph that you get when you explain the first ionization enthalpy of the 3D series from scandium to Zn. So you can see that first it is slightly increasing, then there is a small decrease. This is in the case of Mn, Fe and all, and it generally increases to Zn. Here I have given the atomic number down. So the highest is for atomic number 30, which is your Zn. Now let's see what will be the change in the electronic configuration after taking one electron. When you take one electron, the electronic configuration, there's a change. What happens? All of them are becoming M plus. When they become M plus, the outer electron is gone, isn't it? See, in all the cases, outer electron is gone. Now what is the second ionization? Second ionization enthalpy is the energy needed to take the next electron. You're going to take the electron from M plus or from the scandium plus, titanium plus. So it is from this configuration you are going to take the electron. So now you just move on with the electronic configuration from scandium to Zn. See in chromium, Cr plus, it is having R-full stability. More than 4s, 3d5 is stable. Why? It has an exchange energy, it has an extra stability. Now similarly, when you reach copper, it is having 3d10. All the others are having 4s1, but copper plus is having 3d10 in the outermost. Very difficult. So in case of chromium and in case of copper, you need more energy to take. Why? Because in chromium plus it is argon 3d5 and copper plus it is argon 3d10. So you need a more ionization enthalpy than expected. So we'll see how the graph is. This is what I explained, the ionization, second ionization enthalpy. M plus changes to M2 plus. This is the graph. Just have a look at this graph. In this graph, the peak is seen at 24, that is chromium. Another peak you can see near to 29 because Zn is having a lower ionization enthalpy, whereas copper is having the higher ionization enthalpy. Why? It's a very important question. Why is a variation seen in the second ionization enthalpy? Or why do you say that the second ionization enthalpy of chromium and copper is very high? It's actually a board related question. So for that, the main important reason is electronic configuration. From chromium, you're going to take the electron from D5. For copper, you're going to take the electron from D10. Next, we'll see what is this third ionization enthalpy. Now, after taking the second electron, what happens to its charge and how is it? It's scandium 2 plus, titanium 2 plus, vanadium 2 plus, like that, all are in M2 plus state. If they all are in M2 plus state, there will be change in their electronic configuration. Now, understanding the electronic configuration, what do you see in this electronic configuration? We see that we have to take the electron from M2 plus, that is 3d5, our full stability. Zn2 plus, 3d10, completely full stability. So the third ionization enthalpy, now we are going to take the third electron. So third ionization enthalpy will be high for Mn and Zn, purely based on electronic configuration. Now we will see the graph for the third ionization enthalpy. Third ionization enthalpy is the energy needed to remove the third electron. So now from M2 plus, it's going to change to M3 plus. This is the graph we can explain. In this graph, just see the highest is for 25. Who's 25? 25 is your Mn. And very high ionization enthalpy is for Zn, which is atomic number 30. The reason is half-filled and completely filled stability. Now, when we just see what will be the configuration of scandium 3 plus, titanium 3 plus, vanadium 3 plus, they have used the third ionization enthalpy now. Scandium 3 plus is completely stable. Scandium 3 plus is more stable than scandium because just see the configuration, it is argon. Most of them are stable, but just see in the case of Fe3 plus, it's a usual question that we'll discuss even in the question session. Fe3 plus or Fe2 plus, who is having more ionization enthalpy? How can you tell that who is having the highest ionization enthalpy? Whether Fe2 plus or Fe3 plus. When it is Fe2 plus, it will be argon 3d6. Fe3 plus is argon 3d5. So, third ionization enthalpy is needed in order to make Fe more stable. So, Fe2 plus changing to Fe3 plus needs only little ionization enthalpy because once it's changed into Fe3 plus, it is forming a stable configuration. Next topic is oxidation state of the 3D series. We have discussed now the ionization enthalpy. Now we are moving on to the oxidation state. Here also we are considering the oxidation state from the electronic configuration, because they have the ability to lose the electrons. All are metals generally, so they have a tendency to lose electrons. So I'll just show you which are the possible oxidation states in the 3D series. Here's scandium, configuration of scandium, you know, it is 3d14s2. When it gives all the 3 electrons, it forms a stable oxidation state, that is +3. Scandium always +3 is stable. Now when you take titanium, titanium is having two electrons here, 2 electrons here, you can give all the electrons, that is 4 plus, titanium 4 plus is highly stable. So titanium can show from +2 to +4. In case of vanadium, it can show from +2 to +5. +5 means again noble gas configuration. Chromium can show from +2 to +6. Mn, highest oxidation state. See the number of oxidation state there, +2 to +7. Why is it happening like this? Some of them are showing only very few. When you reach the middle, they are having a lot of oxidation state, more number of oxidation state. Just see again when you check the ion configuration also, coming down the number of oxidation states are decreasing. This is one important point, that is when we move along the 3D series, the number of oxidation state in the beginning is less, then the number is more, then again it is less. That is at the both ends, that is at the left side and even the right side, when you consider both ends, the number of oxidation state is less. Why is it so? In the first case, that is from scandium, titanium, vanadium, the number of electron is less. Scandium is only having 3d, 1, 4s2. Just see, one electron is only there in D. So as it is going down, only the number of electron is increasing. So we see less number of oxidation state because the number of electrons in D is coming down, or you can see that we can tell that the number of D electrons in scandium is low than your chromium. Or we can explain in a different manner. At the end, you can see the number of D electrons are lesser. Coming to the middle, the number of unpaired electron is more. But when you reach the other end, that is your copper, Zn and all, the number of electrons in that will be more in number, but available D orbital is less. So one end, the number of D electron is less, the other end, the availability of D orbital is less. But at the center, you see more because there is more number of unpaired electrons. Now, in the oxidation state, we have found that in the one side, the number of oxidation states are lesser, and when you move to the other side also, the number of oxidation states are lesser. But at the center part, the number of oxidation states are more. Why is it like that? This is because the number of electrons in scandium and all is less in D, whereas there are more number of electrons at the center, and when you reach the end, that is copper, Zn and all, the number of electrons are more, but availability of D orbital is less. So here we can see that maximum oxidation state are seen at the middle of the series due to an increase in the number of unpaired electrons in the D orbital. Mn is having the highest oxidation state because there is more number of electrons in the D orbitals. Now in the extreme left, you can see the number of oxidation states are lesser. This is because the electrons in D is less. The extreme right, the number of oxidation state decreases because again the number of D orbitals available is less. Now we will talk on about the stability of oxidation state. When we talk about the stability of oxidation state, as I told you earlier, due to this exchange energy, D5 and D10 have extra stability. And when it is D0, it is having again an extra stability because of the noble gas configuration. Now when we see the configuration here itself, just see when you are taking the electrons, if you are having Mn2 plus, it will be having D5 configuration. So it is having extra stability. Similarly, when you take copper, if it is copper plus, it is having D10 configuration, it is having extra stability. Similarly, scandium, if you take all the 3 electrons, it will be having the noble gas configuration. So scandium 3 plus will be more stable than scandium. So like that, we can tell that stability of the oxidation state can be due to D0, D5 and even D10. Now variable oxidation state. Now in your P block chapter and in the other sessions, we have studied that inert pair effect is there. Inert pair effect means lower members will have, that is the coming down the group, you are having heavier elements. So the lower number of oxidation state, or if you are having, if a group is having +3 oxidation state, the heavier members will having lower oxidation state. That is, they will be having +1, +2 like that, lower in oxidation state. This is because coming down a group, due to the intervention of D and F orbitals, the S electrons will not take part in bonding, whereas the P orbitals will only take part in bonding. So the reluctance of S to take part in bonding is called inert pair effect. But when we come to D block elements, there's a variable oxidation states are seen. And for heavier elements, you can see that the higher oxidation states are stable. This is just the reverse of inert pair effect. For heavier elements, the higher oxidation state will be stable. Here we will see the variable oxidation state. This because you are having incomplete D orbitals. So Mn and all is showing +2 to +7 oxidation state. Now another thing what I explained now, just the opposite of the inert pair effect, that is group 6. Group 6 you are having chromium, molybdenum, tungsten. When you are coming down, what happens to their stability of the oxidation state? +6 is a stable oxidation state for molybdenum, tungsten. This is because heavier elements will have higher oxidation state. But in case of chromium, it's slightly different. It's a lighter element. It will be more stable in +3. It is stable in +6 but more stable in +3. This +6 compounds will undergo reaction and form +3. So we generally tell that chromium +6 form, that is in dichromate, is a good oxidizing agent. +6 accepts electrons and changes to +3. Why is it happening? Because chromium is a lighter element, so it will be stable in lower oxidation state. Next point is high oxidation state. Transition metals show high oxidation state in their oxides and fluorides. Why is it like that? They show high oxidation state in their oxides and fluorides because oxygen and fluorine are small in size. If they are very small in size, they are highly electronegative. So when transition metals make a bond with them, all the electrons are taken by this oxygen and fluorine and they will come in the highest oxidation state. Among the oxygen and fluorine, oxides will be having the highest. That's a peculiarity of oxygen to make multiple bonds with a metal. So here transition metals show high oxidation state in their oxides and fluorides because with oxygen and fluorine they are having very small size. Now among the oxygen and fluorine, oxides have highest oxidation state, presence of multiple bond. Here you have an example, manganese F4 and Mn2O7 where Mn shows +4 in fluorides and +7 in their oxides. Why? Oxygen is ready to make double bonds, multiple bonds. This is the last point of the oxidation state, which is something a very important point. Even you study this when you go with higher levels of chemistry. That is zero oxidation state. What is a zero oxidation state? A metal is having a zero oxidation state. Is it possible? Yes, when a metal makes a bond with carbonyl groups. For example, if you are having a CO group, CO has a tendency to have pi electron acceptor. It can accept electrons. What is a CO? Carbon monoxide. In carbon monoxide, carbon has a lone pair. That is why we tell you should not take in carbon monoxide. That lone pairs will make a bond with the iron in the hemoglobin and you feel even suffocation in breathing. That's a peculiarity of CO. It's not like your carbon dioxide. So here CO is ready to give that lone pair. At the same time, it accepts that pair into it. So it gives the electrons to metal. It forms a sigma bond. Then the metal gives back that electron to CO into its anti-bonding orbital. It's a pi anti-bonding orbital. So the taken electrons are again given back. And that bond that is formed, the back bonding bond, is a pi bond. So there's a back bonding effect or a synergic effect happens from a metal to back to the CO. Because of that, the MC bond is very strong and the metal comes in a zero oxidation state. Here the CO you call as the ligand. Why do you call it as a ligand? Ligand is someone who gives a pair of electrons to make a bond. That type of bond you call it as a dative bond. So ligand, the ion of molecules which is bonded to the central atom, is called as an ion. And if for example you have taken here NiCO4, the ligand is CO, it makes a MC bond, that is a sigma bond, and then the CO gives back, that is you get the electrons back from the metal which again forms to the vacant antibonding orbital which is forming an MC bond, which is a strong bond, and this effect is generally called as a synergic effect. Another examples here is FeCO 5 times and nickel CO 4 times. In both cases, Fe and nickel are having zero oxidation state. Now we will discuss a few questions based on the ionization enthalpy. The first question is, second ionization enthalpy is more for chromium and copper. Why? We studied the second ionization enthalpy means you are going to take the electron from the stable electronic configuration of chromium and stable electronic configuration of copper, the D5, D10. So it's just for 1 mark, you just have to write based on the electronic configuration. Second question, explain the variation in the third ionization enthalpy. For this, what is third ionization enthalpy? You are taking the electron from M2+. So when you take the electron from M2 plus, which are the ones who are having stability? Mn and Zn. So when you have to show the graph where you have a peak at Mn and Zn. Next, we will move on to the other questions of ionization enthalpies. The ionization enthalpy of Fe2 plus or Fe3 plus, which is low, justify. So very, very important question. Fe2 plus or Fe3 plus, who is having lower ionization? Fe2 plus is argon 3d6. So if it gives that one electron, it forms a stability very fast, which is the argon 3d5. So the ionization enthalpy of Fe2 plus will be lower. Now third ionization means you have to take again electron from the, you are going to take the next electron, that is not the third, again you are taking from Fe3 plus. To take the electron from the Fe3 plus means again more energy, it is not possible. There is no possibility to take the electron from D5 again to make it as D4. And you know that for iron Fe2 plus, Fe3 plus are the stable configurations. Explain the variation in the first ionization enthalpy of the 3D series. Similarly, just write the electronic configuration, draw the graph and explain where you see the high ionization enthalpy. So these are the general questions that is asked based on ionization enthalpy. Now we will see what are the questions that is asked generally based on the oxidation states. Transition metals show highest oxidation states in their oxides than in their fluorides. Just a 1 mark question or give reason question. This is because oxygen has the ability to make multiple bonds. That is the main answer point or the answer key for this question. Another question is the +6 oxidation state is more stable for tungsten than chromium. Why? Tungsten, we told that heavier elements have higher oxidation state. Next is chromium is a good oxidizing agent, justify. Why? Chromium +6 will change into +3 because it's a lighter element, so its oxidation state +3 will be more stable. So it's a good oxidizing agent. When we consider the fourth question, that is the oxidation state of nickel in NiCO4, it is 0. Why is it 0? Because the CO has a peculiarity, it is a pi acceptor ligand. So it takes electrons back to the pi antibonding. So the oxidation state will be 0. Another question is titanium 2 plus or titanium 4 plus, which is more stable? The most stable is surely titanium 4 plus because it is having the noble gas configuration. This is a similar question which is explained earlier. In oxides and fluorides, transition metals have high oxidation state. Why? Because oxygen and fluorine are very small in size and they have high electronegativity. So by this we will come to the end of the questions. So we will just see what are things we have discussed today. The main points are, we have explained the first, second, third ionization enthalpies. We have explained the reason for the stability of higher oxidation state of the oxides and fluorides. We understand what is synergic bonding. That's a new term. It's a synergic effect or synergic bonding, or even you can call it as a back bonding. We identify the reason for the stability of higher oxidation state. Hope you have all followed the questions that we have discussed. Try to do more questions based on these ionization enthalpies and oxidation state. Thank you.